All right, let's get started here. Good morning, everyone. Welcome to Autodesk Virtual Academy. I'm Nigel Umbayek, one of the customer success managers here at KETIV Technologies, and your guys' hosts for today and every other day's AVA. So welcome. And today I'm joined by Cameron Whetten, one of my colleagues here at KETIV. Cameron, how's it going?
Going great. How are you, Nigel?
Good, good. So Cameron happens to be out of his home office, so he's not in the studio with me today. Definitely wish he was here for this session. We do miss you out here in California, Cameron. But Cameron's going to be going over something I think really powerful and really, I guess, fundamental when you look at some of the core Inventor functionality, and that's leveraging parameters in general and using math in terms of the parameters editor as well. This is something that me and Cameron have spoken about in the past, and he mentions, hey, this is something that I think is like very day one Inventor that is really core functionality that people need to know about to be able to leverage the tool to its most powerful capabilities, which is pretty extensive. So if anyone has any questions at any time during the webinar, go ahead and post those into your respective chat panels. We'll go ahead and answer those when we get to the Q&A section. Anything else you have there to add, Cameron?
No, that sounds great. Thanks for the intro.
Absolutely. So without further ado, let's go ahead and get started here with Inventor, parameters, and the power of math in them. So Cameron, go ahead and take it away, and we'll see you on the other side.
Okay, great. Thanks, Nigel. All right, welcome everyone. Like you said, we're going to be talking about parameters and using math to control those parameters. So parameters are the backbone of Inventor's design power, and learning to control those parameters is the first step to unlocking that power. So today we're going to cover the basics of creating formulas to control Inventor parameters. And fundamental to this is understanding how units are important and how to set them up properly so that our formulas give the correct results. We will also review the various math functions that are available to us and how to use them. So you can use equations or formulas. I'm kind of going to be using equations and formulas, those two terms, interchangeably throughout. They really kind of mean the same thing when I'm talking about it here. So, but you can use equations wherever you can enter a numeric value inside of Inventor. So for example, you can write equations in the Edit Dimension dialog boxes. And to demonstrate what I mean there, I'm going to go ahead and switch over to Inventor. And I'm going to go ahead and start a brand new sketch here real quick. Draw us a quick rectangle. And I'm going to add a sketch dimension to this line. And when I place that dimension, this Edit Dimension dialog box pops up. So that's what I was talking about. And by default, it just pops up this static value that happens to be the current measurement of that line there. And that's fine, but we don't have to stick with just this static value. This is one of those places where we can go ahead and enter a formula to control this parameter. So I'm going to go ahead and just type something in here really quick so you can get just a quick example of what I'm talking about. So 2 times 6 plus 3, right? Simple little formula that we can enter in there. And just to kind of elaborate on what formulas can do for us, why they're important, and why we might want to use them. They can help us calculate the value of dimensions, like what we've got here, this simple little formula. They can also help us link parameters together, so we can leverage Inventor's parametric capabilities. And they also help us record the logic that went into determining the value of a dimension. So, for example, I've seen people using Inventor, and they'll create a sketch like this and place a dimension, and this Edit Dimension dialog box will appear. And they need to figure out what value they need to put in there for that dimension. So I've seen them reach across the desk, pick up their calculator, start punching in numbers into their calculator, and hit equals to find the value of some dimension. They take what's the value that the calculator gave them, then they come in here to this Edit Dimension dialog box and just type the dimension in here. And I just have to say to them, hey, did you know that formula you just punched into your calculator there, you could have just typed that right here into the edit dimension dialog box, and Inventor would do the calculation for you and give you the answer you're looking for. And not only that, it also remembers the formula you put in there. So, you know, if you made a mistake, you can go back in, check your formula really easily, see what you typed in. If you find a mistake, you can fix it really easily, and then you're good to go. And it's also nice that it remembers the formula for later. So if you have to come back to it later, you can see what, instead of just having a value there and not knowing where it came from, you can see the thought process that went into creating the value for that dimension. And again, it's also, for that same reason, it's useful for other people who may come and look at your work at some point. They can see what your thought process was for arriving at a value, instead of just having a value, static value there, and having to guess what you did to get that value. So there's a lot of power here in using formulas. Another place you can enter formulas is if you're creating features. As you're familiar, that any place where you create an extrusion here, you can just put a formula in there as well. So I could do 5 divided by 2 plus 7, and that's going to calculate the answer. And go ahead and put the formula there. And last but not least, in the parameters editor. And this is where we're going to be looking for the rest of our class time here today. And as you can see, the formulas that I just created for those two, well, the sketch and the feature dimensions, those formulas are preserved here that you can see. And also, if you add numeric parameters, then you can go ahead and let's make this an angle. I just made that degrees. We'll talk about units in a minute. But we can just put formula in here. Pi radians divided by 5 plus 25 degrees times pi radians over 180 degrees. Okay. We just put a formula in here, and Inventor calculates the value for us. So just as a quick recap, in our parameters editor here, we've got the name of the parameter in this column, the units that are assigned to that parameter. This is where we put the equation, and then this is the answer, the result of that equation, this nominal value. So that ends up, when we calculate all of that out, that ends up being 61 degrees. Okay, so we're going to go and look at some of the different elements of what these formulas that we've just put in here. We'll break that down a little more. But as you can see just from this, that parameters can vary in complexity. From the very, very basic, like these up here, to more moderate complexity formulas here, to very complex. You can have formulas that are 1, 2, 3 lines long or more. Whatever it is that you need, you can put the formulas in here. And you can use them for all sorts of things, like we've seen with features, feature sizes. You can use them for offsets and angles for assembly constraints. Or even more complex things like simulating motion of components. But the basic elements of every formula are going to be your algebraic operators, and that's going to be your addition, subtraction, multiply, divide, that sort of thing. We'll talk about all of those. And also your units and prefixes and mathematical functions. And we'll talk more in detail about each of those. So first, let's go into the algebraic operators. I'm going to switch back to my PowerPoint here real quick. So we can see all of the different algebraic operators that you can use inside of your formulas. Now, algebraic operators, that's not a term we use in normal everyday conversation, but you know what it's talking about here. It's our plus, minus, divide, multiplication, etc., right? But the reason I wanted to show you these is this is actually telling you what symbol to use in your formula, so so that Inventor knows what it is you're trying to do, right? Plus and minus, that's pretty obvious. Multiplication is a asterisk or star character. Division is a // And if you want to raise something to a power, give it an exponent like 2 squared or whatever, then you use this caret, it's the shift 6 key. It gives you that little caret symbol for power. And then, of course, we've got our parentheses for enclosing different parts of your expression, break it into little pieces. And the semicolon is a delimiter for, like it says, multi-argument functions. And what that means is there are some of the mathematical functions that we'll talk about later, like sine, for instance, is a trigonometric function, a sine or a cosine. That function, it has one argument. You take the sine or the cosine of a number, and then it gives you a value, right? So it has one argument. The number that you're taking the sine of is the argument. But there are some functions that have multiple arguments, and you have to be able to distinguish between them with a delimiter. And in normal, outside of Inventor usage, like in other programming languages or other programs, delimiter is usually a comma. You separate those arguments with commas, but you can't do that in Inventor because comma in some regions is actually the decimal divider, decimal point. So they couldn't use commas, so they used a semicolon instead. So just keep that in mind when you get to use those functions later. You're probably going to want to use a comma because that's what seems natural, but just keep in mind that it should be a semicolon. And you'll see those functions later that require that. And the last thing I want to talk about here is this floating point modulo. A lot of people probably are not familiar with this. It's not something that's used very often, and it is a little difficult to explain in words. So I'm just going to show you how that works really quick here. I'll switch back to Inventor. And in my parameters editor here, I'm going to go ahead and create a new parameter and call it my modulo. So you can see here, I'm going to make this unitless just for simplicity for now. And the way this works is essentially a modulo function or operator takes two numbers, divides them, and gives you the remainder. So if I do if I wanted to do 5 modulo, and the character I use for that is the percent sign, 5 modulo 2, and the answer that it gives us is 1. So what that's doing is it's taking 5 and it's dividing by 2, and then instead of giving us the answer of 5 divided by 2, which would be 2.5, right? That would be the quotient of those two numbers. It's not giving us that. Instead, it's giving us the remainder, which is basically you take 2, find out how many times it can fit into 5 in whole chunks of 2, which would be twice, which would give us 4, which would give us a remainder of 1 to get to 5. Okay? If you want to learn more about that, you can just look it up. Just Google modulo, and you can learn all about that. But that's kind of the quick summary of what a modulo is. Like I said, it's not something that's used very often, but one thing that it is and can be useful for, the most common use of it is to determine if a value is even or odd. So if let's say you've got some other formula in another parameter or something like this, and you need to know if the result that you get from that formula is even or odd, then what you do is you take, let me show you an example. So let me create a new parameter here called result. So we'll just pretend that there's some other formula that's taking, some of the formula that's computing this result here, and we want to find out whether that is even or odd. Then we would put this in the numerator position, if you will. The first position before the modulo operator would be a result. And then if you want to find out if it's even or odd, you'd want to take it a modulo of 2. You can put other numbers there for other reasons, but if you're wanting to determine if something's even or odd, you're going to take a modulo of 2. And if the result is odd, like in this case where it's 7, the modulo is going to return a value of 1. If it's even, I'm going to change that to 8, and that's going to give us a modulo of 0. Okay, and it's always going to be that. If it's even, it's always going to be 0. If it's odd, it's always going to be 1. If you're taking modulo 2. Okay, so that's the most common usage I've seen for the modulo operator. All right. let's talk about the next, probably the most important thing of learning how to get the results you need from formulas inside of Inventor is understanding the order of operations. Inventor uses the order of operations to compute its results. So if you want to predict, if you want to be able to predict and control the results you get from an Inventor formula, you're going to need to understand the order of operations. And you're probably familiar with this. You've at least heard of it in a math class at some point in the past. But back then in a math class, this was all theoretical, right? Now, here is where it becomes practical and important. So let's just review this really quickly. The order of operations, as shown in this table, goes in order from top to bottom. So Inventor is going to evaluate everything in parentheses first. And if there are multiple sets of parentheses, it evaluates from the innermost parentheses to the outermost parentheses. So for example, in this, let me turn on my highlighter here so we can see, highlight some stuff. So this is the innermost set of parentheses here. So it's going to evaluate this first. So it's going to do 15 degrees times 2. The result would be 30, right? So it's done that first. Now we go outside the parentheses and go to this next set of parentheses. And we're going to have to evaluate the next set there. So we take the sine of the 30 degrees, and then we add on pi over 4. And then finally, we take what's outside of those parentheses, and then take the entire result from inside there and multiply it by 4. Okay? So that's how parentheses are evaluated first. The next step is going to be exponentiation, or squared powers. And so another example here, we've got parentheses. So we'd have to do everything inside parentheses first. So we take the width plus the 5. So it's not going to be 5 squared and then add on the width, right? We have to do what's inside the parentheses first. Take the width plus 5. And then we go outside the parentheses. And we've got a multiplication by 2 here, but we don't do that first because multiplication's later. That's down here at the bottom, right? So we don't do the times 2 first. We do the square first. We square that whole result of the width plus 5. And then once we're done with the exponentiation, then we go down the list and we say the next is multiplication, and then we do that. Okay. And then next is negation, or in other words, just making a negative, making a number negative. And you can see in this example, we've got 2 situations. We've got one here, one outside the parenthesis, and one inside. So in this case, we are going to, again, do what's in parentheses first. So that's this whole expression. So we've got an addition here, but addition's last on the list. So we don't do the 2.5 plus the length and then make it negative. That's not how it works. We have to do the negative first. So we make this a negative 2.5, and then we add the length. Okay, then we're done with what's inside the parenthesis, and then we come outside the parenthesis, and what do we do next? Well, we go down the list again, and we do exponentiation first, right? That's the next on the list. And so we don't do the negative next, we do the square and then the negative. And this is important because you get completely different results. If you do the negative first and then square it, whenever you square a negative number, it always comes out positive, right? But in this case, if we square it first and then apply the negative, we get a negative value. So we get opposite results if we go in the wrong direction. So we do want to be careful on that. Make sure we follow the order of operations always. Okay, so square and then negative. The final result would be negative. And then next is multiplication. That's pretty straightforward. I think we've kind of covered examples of that so far in the previous. And finally, addition or subtraction. Let's just take one last look at this last formula here. We'll go down the list. We've got a negation. So that's going to happen first. We take a negative 2.5. And then we've also got a multiplication. So we're going to want to take this 0.35 times the base parameter and get the result of that. And before we do subtract it off of the height and then add on this negative 2.5 here. So again, if you do the order of operations wrong, you're going to get a wrong result. And so it's very important to understand. All right. Enough said on that, I think. Let's talk about units. And we'll switch back to Inventor for this because the list of units is long. I couldn't fit it onto this one slide. The best place to look at the different types of units that Inventor will interpret is to actually open up your parameters editor here and go to a user parameter and click on the unit column for any one of your unit parameters. And that's going to pull up the list of different types of units that are available. And so here we can see the list of the different types of units. And this list is not complete. There's some here that it doesn't have, but we'll talk about those in a second. But let's just take a look underneath some of these different types of units, like length type unit. And you'll see the different units that are available for that. So you've got your millimeters, centimeters, feet, inches, etc. Time, you've got seconds, minutes, hours. Let's see, volume, liters, gallons, etc. Lots of different types of units available. Now, these lists of units are not complete. They don't have every type of unit you could possibly use for length. As you'll see, like maybe you need nanometers for some reason. You'll see nanometers is not in the list. We've got meters, centimeters, and millimeters, but no nanometers. But that doesn't mean we can't use it, that Inventor won't understand it. But it's just a unit with a different prefix, right? So let's go all the way to the bottom here. You'll see there's this prefixes category. So if we open that, these are all the different prefixes that you can use to create those different scales of units, if you will. And if we wanted to do nanometers, you'll see there's nano on the list there. And what's in parentheses here is telling you exactly the character you should use in order to use that prefix. So if we wanted to do nanometers, we could go up here and look, okay, for meters, it's just M, right? Most of these are going to follow the SI convention. So if you're familiar with those, you can be pretty comfortable in using them. But if you're not sure what the unit is supposed to look like, you can always come in here and take a look and see, M for meter, IN for inches instead of, FT for feet, etc. So if we want to do nanometers, we could just double click that and it'll insert an N for us. Then we can come up here, double click M, and it'll insert, or you can just type it in NM. And as you'll see, Inventor's just fine with that, puts NM in there, and that's good to go. So you can combine these prefixes pretty much with any of the units that are in here. I haven't actually tested that with every single one of them, but I'm pretty sure it probably works for every single one, except for unit list. That wouldn't make sense. I guess we should talk about that. So there are some things that don't have units. So if we were just talking about the count of something, like how many pens do I have on my desk? There's not a unit there. It's just a count of each, right? So Inventor uses it calls it unitless, and the symbol is UL. And you'll see that frequently. A lot of times, especially Inventor will automatically insert those for you if you haven't typed them in, but that's what that means. UL is unitless. And the other types of units that you don't see on here, like torque, for instance, is not on here because it's really a composite unit. And which basically means you're taking other units that are on here and combining them together to make the composite unit. So like for example, torque, if you wanted to, so a torque is a force times a distance. And so if we could go to force, if we wanted to do foot-pounds, then let's go to distance first, or length. And we can grab feet, FT for feet, we'll drop that in there. And then it's multiplied by force, and we'll grab pounds. Okay, so foot-pounds for torque, so hit OK. And Inventor's fine with that, it likes it. It's not going to throw an error message, but it does change just kind of the layout of the unit to what it prefers, LB force space FT, and that's fine. It'll do what it prefers, but it still understands, it's completely understood what I inputted. And you can do that for any type of composite unit you might need. Some of the common ones are going to be like area. You might not think of area as a composite unit, but Inventor is thinking of it that way. So if we go to area, you might expect to find your common area units in here, like square inches or square millimeters or something. But if I expand that, you'll see those aren't even listed. The only one we've got here is circular mill. And that's just because Inventor is looking at those as a composite unit. It's really just if we wanted square meters, then we could just do meters times meters. And then it's likes that just fine. It does change the layout a little bit to M-2. That's what it prefers. But it totally understood M times meters, or yeah, meters times meters. So, so your area is going to be that way. Volume is going to be the same thing. If you need cubic inches, cubic centimeters, whatever, just do the same idea. You could just do cm squared or cubed. And we've got a volume unit there. Okay. All right, there's a lot to talk about with the units here. You'll see that newly created parameters. If I add a new numeric parameter, it's going to be assigned a unit by default. And it's always going to be assigned a length unit. But in this case, it's assigned inches. And that the unit that it defaults to is controlled by the document settings. Let's take a real quick look at that. I'm going to go ahead and close my editor here and go to Tools, Document Settings, and go to the Units tab. And this is what is controlling the unit that it uses by default. Okay, and so I could change this to millimeters if that was going to be the unit I wanted to work in. And we'll do that and go back to our parameters editor and see what's changed. So you'll see this parameter that I made here, it's a user parameter and it was already set to inches, so it doesn't change that. But you'll notice up here, it did change these. These model parameters were defaulted to inches, but when I changed it, it changed them to the default of the document setting. It didn't change the value itself as far as, it didn't change this to 2 millimeters or this to 5 inches and 5 millimeters and 7 millimeters, because that would actually change the dimensions of the part itself, would be horrible. But what it does, it leaves those in the units they were set to, but then it does the conversion for you to tell you what this value computes to in millimeters. Okay, so it does that for model parameters, but not for user parameters. These ones are going to stay whatever default they are, but if I create a new one, it's going to default to millimeters now. Okay, I'm going to go ahead and switch that back. Oops, go back to document settings. Switch that back to inches. Okay. All right, so if you are entering a formula into a parameter or an edit dialog box or something, like this one up here, if I just enter 2 times 6 plus 3, I'm not specifying units, and that's okay. I can go ahead and hit enter. Inventor has to work in units. It just does. That's how it works. So even if you're not writing units in there, Inventor is assuming that there are units associated with those numbers, and it's going to do its best to read your mind and assign units to those values. And if you're writing a simple formula, Inventor's pretty good about getting the units right, but you do always want to review to make sure it's getting the units right. So in this case, maybe what I really meant was I was just wanting to take 6 inches plus 3 inches and then doubling it. And that's not what I'm getting. Well, I guess the result is the same. But if I want the units to be expressed in the way that I was thinking about it, Inventor assumed the wrong thing, right? It assumed this was inches and that this was unitless. So if I wanted to, I can just come in here and change this to unitless and make sure I change these to inches. And then in this particular case, it ends up with the same result. That's not always going to be true. It depends on what operations you're doing. But at least now it makes sense in my brain what I was trying to do there. And again, that would probably make more sense to someone later down the road if it was written out this way, if that's what you intended. Okay, so another important thing is that your units in your formulas must be consistent. meaning you can't really mix unit types. Or if you do, you have to do it in a specific way so that the result ends up being in the units that the parameter expects. So let's take a look at this formula up here, right? So we've actually got a couple different unit types going on here. We've got RAD, that's radians, which is an angular unit. We've got unitless. We've got degrees, another different type of angular unit. But all of this, when it all works out, the result has to end up in degrees because that's what this parameter expects. If it ends up being something different, it's going to throw an error. So if I just add on 1 millimeter, you'll see that it turns red, and that's Inventor telling us, okay, there's something wrong with this. And if you're not sure what is wrong with it, you can hover over, and it should give you warning unit specification mismatched, right? So it's telling us that there's a unit problem. And that's obvious, right? We try to combine angular units and add in a millimeter, and that just doesn't even make sense, right? 61 degrees plus 1 millimeter, what does that even mean? It doesn't mean anything to us, it doesn't mean anything to Inventor. If for whatever reason you needed to do something like this, you'd have to do some unit cancellation and multiplication in order to get this to work out correctly. Like for example, maybe we needed to use a parameter here. We want to be adding on 1 degree or whatever. You could just do that. But in this case, let's say we actually need to add in one of our parameters, A3, which is in millimeters. Then we'd have to do some unit cancellation. So we'd have to basically remove the millimeters by dividing by 1 millimeter. That cancels the millimeters from A3, but it's still, that just gives us a unitless value, which again, adding on to degrees doesn't make sense. 61 degrees plus one what? Not 1 degree, but one car, 1 donut. What? Doesn't make sense, right? So we also need to tell it, in this particular case, we want that to be in degrees. So if we just times it by 1 degree, then the units work out and Inventor can calculate it and it's just happy with it. Now, this is not a situation you'll run into very often. I find that in almost exclusively all the formulas that I write, the units, if I've put the thought into making the units, assigning the units instead of letting Inventor do it automatically, if I make sure that the units are assigned correctly, they all just end up right in the end. It kind of works that way in real life. If you're going to add a bunch of stuff together, these are all lengths you're adding together, so I need to make sure they're all length type units. You know, you can mix units like inches and millimeters, and that'll work just fine. Like down here, I could add 1 millimeter plus 1/4 of an inch, and just type it in there like that. I don't have to do the conversion. I can let Inventor do that for me, and I do that all the time. I think that's one of the great things about all this, and it will do the conversion for me. So that's fine. You can mix units of the same type, and Inventor will do the conversion for you. But you can't mix units of different types. And just like, I mean, if you're figuring out the geometry in real life, it's just going to work out that way. There are very rare situations where you need to do this kind of unit manipulation. But I will show you an example of that in a little while. All right, so the reason these are red is probably some unit mismatches again. This one in particular, so if we hover over it, it's telling us, okay, in this case, it's being a little more specific. Instead of just saying unit mismatch, it's actually telling us, okay, it's expecting cubic centimeters, but it's found unitless, right? So this parameter is set to cubic centimeters, but we've given it 8 UL, which it doesn't know how to do. Now you have to be careful with this because Inventor will let you, so if I push enter, it doesn't throw an error message and say, sorry, you can't do that, please fix it before moving on. It will actually accept it. And in this case, it is just doing 8. Let me try, I'm going to change this to, let's change that to inches. Okay, so now you're going to see the number that it actually gets is, it's computing a number, but it's garbage, right? 8 unitless converted to inches. What is the conversion rate? You know, you can convert between centimeters and inches, you know, at 2.54 centimeters per inch. There's a conversion factor there, but what's the conversion factor between unitless and inches? You know, that doesn't make sense. There is none. But Inventor is using something for it, and it's reporting a garbage number. So you do have to be careful with your units because you can get bad results. and Inventor doesn't necessarily tell you. I mean, it does have the red in here. That's your indication to say, hey, there's something weird going on here. But you know, if you've just got some automated formulas doing stuff in the background and you're not checking your parameters editor, you know, you could get garbage and not even know it. So you do have to be careful of that. All right. Next thing I want to mention is there are two numbers that Inventor has stored they're called reserved system parameters, but they're basically just well, it's pi, the number pi, and the natural number e are two numbers that Inventor has stored that you can use. They're called reserved system parameters because that means you basically can't create another parameter with that name. Like if I try to create a parameter named pi, Inventor won't let me. Unable to create variable name conflicts with a predefined constant, right? So you can't do pi, and you can't do uppercase E. Same thing there, right? But you can use those numbers like we have in this formula up here. I've actually, if you just by just typing capital PI, you can use the number pi. And it has to be capital PI. If I do lowercase pi, it doesn't. I don't know what that means. So it is case sensitive, but uppercase pi, and I could also do E if I wanted to. Let's go ahead and make that uniless. And if I just type E, there we go, the 2.7182, right? Okay, let's talk about some of the different mathematical functions that are available to us. This is a list of mathematical functions you can use in your formulas. It's pretty long, so I had to split it up into two chunks of a table here on the slide. But you'll see on the left is what you actually type to access that function, and then it tells us what units to expect back from the function and what units the function expects us to supply to it, right? So what's here, this expression in between parentheses. So here we've got our trig functions, cosine, sine, tangent, and we just give it a number or a parameter, another parameter, and it expects the parameter or the number that we give it to be an angle type parameter, so that can be degrees, radians, etc. And then the result that it's going to give us is going to end up being unitless. Okay. And then we've got their inverse trig functions here, inverse cosine, sine, tangent, or arc cosine. That's where the A comes from, A cosine. And it's the reverse of that, right? So the expression that it expects needs to be unitless in order for it to calculate correctly. And the value that it's going to give us back is going to be in some angle units, such as degrees or radians. And we've got our hyperbolic trig functions here, and they follow the same pattern as the regular trig functions. So expect an angle, return unitless. And then we've got the inverse of the hyperbolic, which is same pattern as the inverse regular functions. They expect a unitless and return an angle. Okay. We've also got square root. If you need to do a square root, this is what you type, SQRT. And keep in mind, these are all case sensitive. You do have to do them, and they're all lowercase, so that makes it easy. But they are case sensitive. So square root, if you want to take the square root of a number, you just do SQRT, open parenthesis, and then type in your number. And the expression you can give it can be any type of unit. It will work with any of them just fine. But the unit that it's going to give you back is going to be a square rooted version of that unit. Okay, so that's what it's trying to tell us there. So keep that in mind. Okay, the sine function, not S-I-N-E, but S-I-G-N, is useful for figuring out if a result is positive or negative. Okay, so you've got, again, maybe some other parameter that has a big formula that's doing a big calculation, and you need to find out if the result of that is positive or negative. Then you take your result, put it in for the expression, and it will return a 0 if the result is negative, or it will return a 1 if it's positive. Okay? So that can be very useful for logic functions, either using iLogic or just using in other parameters and other formulas. Units for the expression can be any type of units. It's fine with that, but it's always going to give you a unitless result. So if it's negative, it's going to give you 0 UL. If it's positive, it's going to give you 1 UL. Okay, the exp function is basically raising e to a power, the number e to that we were just talking about a minute ago, the 2.1782 natural number e. It's raising that to whatever power you put in here. So if you want e squared, you just do exp 2 inside of that. It's kind of an unusual function because it's easy enough to just do, e squared and get the same result. So there's 7.389. That's the same thing as exp 2. So there's just 2 different ways of writing that. Not really sure why there's the 2 different ways, but there's probably some specific situation where that's useful. I've just not seen it. Okay, floor, ceiling, and round. These are functions that I use all the time. Very common functions, very useful. But they do have a bit of a quirk, and so it's worth talking about. So the floor function is going to take any number that you give it and round it down to the next whole number. Ceiling is going to round that number up to the next whole number, and round is going to round it either up or down to whichever whole number is nearest or closest. So very useful, but the trick with these is that they expect a unitless number and they return a unitless number. So that can get tricky. So I'm going to switch back to Inventor and show you what I mean. Let's go ahead, and we've got our inch parameter here. Let's say we've got another inch parameter here. Let's make that like 2.35. And let's say I want to take the floor of result. Okay, I just want to round 2.35, round down 2.35 to the nearest integer, right? But Inventor won't let us do it. It's complaining. It's red, right? There's something wrong with that. It's because it's expecting a unitless value, but we're giving it an inch value. And it's returning a unitless value, but we're storing it in an inch, right? So you have to do a little bit of unit juggling here. So basically what we have to do is make result be unitless instead of inches. And the easiest way to do that is to just divide by 1 inch. So dividing by 1 doesn't change the number, but it does cancel out the units and make it unitless, okay? But then again, we have to get it back into inches because floor returns a unitless value. So we just do the same, kind of the opposite, and just times it by 1 inch. And again, timesing by 1 doesn't change the value, but it does convert it back into inches. So then it does like that just fine. So now we get the result we are expecting, 2 inches. Okay, so that's one that's, if you're not familiar with doing this, this is one that's going to catch you for sure. It's caught me a few times over the years until I got used to it. Now I know I just have to write that out each time. And so the ceiling and the round functions are going to do the exact same thing, and you just take the same approach with those. All right, ABS is going to be your absolute value, which just takes whatever the expression is, whether it's positive or negative, and always returns a positive value. And it will take whatever units you like and spit it back in those same units, which is what you'd expect. All right, max and min, these are some of those functions that actually take more than one argument. You can see there's expression 1 and expression 2. And to distinguish between those two, this is where that semicolon comes into effect, right? We were talking about earlier. Instead of using a comma, which is what you might seem natural, you need to use that semicolon there. And this function just it looks at these 2 expressions and figures out whichever one's biggest and returns that value. And then minimum looks at the 2 expressions, whichever one's smallest returns that value. Okay, so it's a useful function for filtering between 2 different values. And the units on that, you can give it any unit you like, and it'll return it in the same units. So what you'd expect there. ln is a natural logarithm, and yeah, it's pretty straightforward, but it does have to be unitless, and it does return a unitless value. So you might have to, if you're going to be using ln, you're going to have to do some unit massaging there, like with the ceiling and round functions. Log is your logarithm. That's going to be a base 10 logarithm. Same idea, unitless expected, unitless returned. POW, power is basically just raising a value. And this is another multi-expression or multi-argument function. You take this value and raise it to this power. So if you wanted to do 5 squared, you'd put POW, open paren, 5, semicolon 2, and that would give you 5 squared. Again, this is another one of those odd functions. It's like, well, I could just type 5 caret 2 and that does the exact same thing. There's probably some specific needs, specific situations where that's useful, and so it was created, but I've never used it. I've always just used the caret operator. All right, random is an unusual little function that will just generate a random number at the time the expression is evaluated. I've never actually used it, but I'm sure there are people who have found a good use for that. But we could just do, what are the units on that? I did not check. Unitless, okay, so I can't have it be inches here. So change that to unitless, type random, and then there's no argument for this function. But you still have to have the parentheses, because if I just type random, it thinks I'm talking about a parameter named random. But you do have to put the parentheses in there, but you put nothing in between them. And then when I hit enter, it's just going to give, and I'm pretty sure, at least from all the testing that I've done on this, I think it gives you a random number between 0 and 1. I've never seen it outside of that range. So there's, again, probably some specific use case envisioned for that. There you go. It's an interesting function. I'm not sure exactly when it reevaluates. I think now it'll be different if I come back. Anytime you force that to recalculate, it comes up with a new random number. I don't know. It's interesting. I don't want to spend too much time on that. All right, the last function here is another unusual one. It's called isolate. And basically, what it does is it allows you to change the units of an expression. So you type your expression here, and let's say you have it in inches, and you could convert it, and then you put IN there for inches. Well, I think you'd actually put 1 IN. Well, we'll do a quick example of this. But from inches to maybe millimeters, and you could change a number from inches to millimeters using this function. It's really unusual. Again, one that I've not really ever used, but what units does that return? Any. So, oh, well, it returns the one you want to convert to, of course. So let's do one here and millimeters, and let's say we've got 5 inches. We want to convert from 5. Let's use result as in inches, right? So let's use another one of our parameters. So we're going to do isolate and then result. And so we want it to be in inches, but we don't want to convert to inches or to millimeters. So we don't want 2.35 being converted into whatever that is in millimeters. We want 2.35 millimeters to come out of it. Then we put the result we're starting from, which is inches, and then the units we want to convert into, which is millimeters. And yeah, I don't know. Clearly there's something about that I don't understand, because I was not expecting that number. That's an unusual function. Like I said, I've never used that. If you can find a use for that, great. But that's all the time I want to spend on that. A few last things I want to talk about is some syntax. Let's go back to Inventor. And you'll see that it is possible to have all of the errors we've seen so far have been related to units not being correct. But you can also run into errors with syntax not being correct. Like, for example, this one, if I didn't put the parentheses in there, it doesn't like that. That's a syntax error. And usually that's the error message you'll get with your syntax error is cannot evaluate. It doesn't know what you mean, and it can't read your mind. So, you know, so if I just type like +6, it doesn't like that. That's not valid syntax. It doesn't know what that means. Even though we might be able to interpret that as just being +6, that's not how Inventor reads that. Or you could do, if you just have like, if you have parentheses that are wrong, like you've got too many or too few open and closed parentheses that don't match up, then you're going to get a syntax error. So you'll have to go through and start counting parentheses to figure out which one's missing and where it is. But some common syntax mistakes that you'll run into, let's let's take a look at, oh, and if you try to exit out, in this case, it's not going to accept it and give you some garbage number. It's just going to say, I don't know what you're trying to do here. I can't evaluate this. I'm going to throw up an error message, and then it's basically going to undo whatever change you just made. Okay. So I'm going to type this in here, 2 plus 3 cubed. Okay. So this is red, and this is not necessarily a syntax issue, but this is a units issue. It doesn't really know what to do here because it's going to try to assign default units like it did for some of these simple formulas we did earlier. Well, the problem is it's going to try to assign this to be inches, which would be fine because this is in inches. And it's going to try to assign this to be inches. Well, what it actually does, it actually assumes both of these are unitless, as you'll see if I go ahead and hit enter. Tries to assign this unitless, this unitless, because it can't decide what to do there. But the result ends up being wrong because we get 2 inches plus 3 with no units, and that doesn't match up. We've got mismatching units, that's a problem. So that doesn't make sense. But if we just go here and try to type inches in, that doesn't work either because it's important to know that the exponentiation, the power operator, is applying to the units as well as the number. So it's going to square 3, which will give us 9, but it's also going to square the inches and give, or not square, sorry, cube. And so it'll give us 27, and then it'll cube the inches and give us cubic inches. And so now we've got 2 inches plus 27 cubic inches, which just doesn't make sense. And so it's going to throw an error message there. So there's not really a good way to write this. I mean, this formula really doesn't make sense in these units, so we'd have to do something else to figure out what to do there. Excuse me. Another example of the units being applied is if I type this out, 2m squared, well, maybe I should be, I'm going to change my units here to square meters so I can complain about that.
Quick, Cam,
let's just,
Cam,
yeah.
if you want to wrap up here, there's some questions I want to definitely get answered before we run out of time. So let's sort this out and then jump into questions, just letting you know.
Yeah, perfect. This is the last thing I was going to go over. So, so in this case, I've typed out 2m squared. If you intended for this to give us 4 square meters in the end, it's not going to. If I hit enter, you'll see it's actually giving us 2 square meters because this squared here is not so much the squared operator. It's not 2m squared 2ul, right? That's not what that means. This squared is actually part of the unit designation itself. This is just saying that we've got 2 square meters, right? 2 square meters. If we needed the answer to be 4, we'd have to make sure we enclose that in parentheses. So it actually squares the meters as well. Then we get the 2ul, and the result we get is 4. Okay, so that's that. One last thing I wanted to mention is the tables that I had that I've been showing in here. You can look those up in the Inventor help documentation. If you just go to help, and when it pulls up the Inventor help, if you just type functions, then what you're looking for is right here, functions, prefixes, and algebraic operators. And basically everything we've gone over here today is going to be in here. We've got all the tables for all the functions, the units, operators, all that stuff is there. So if you didn't happen to take notes today, you're in luck. Okay, that is all I wanted to go over. Nigel, if we've got some questions, then let's get going.
Let's jump through these real quick. Thanks again, Cameron, for that. So real quick, question came up pretty early. I just want to go over it again. What's the best way to get to the parameter editor? So there's one way, which I use all the time, which is to hit the function button at the top next to that plus button. That's one way.
There's also the manage tab.
Yep.
It's right there, same thing there.
And then
I use a keyboard shortcut that I've assigned.
Is it Alt 2, Alt 3?
That's what I use. I don't think that's standard, but that's the one I use, Alt 2.
I set it up on my keyboard. I forgot which. I think I use a macro key on my keyboard to do it. But yeah, so that's one way to do it. So that's the first question. We'll sort that out. Let's see here. Could you use the modulo to get inches from a decimal foot value? So No, there's ways to do that without doing modulo. You just have to convert it, right? And it's just all math at that point. It's just unit conversion.
Yeah. That would just be converting units, maybe using a ceiling or floor function to chop off the decimal part, because that would round to the nearest whole value.
Yeah, and that brings up another question too. Sorry, Cam, go ahead.
I was just going to say the modulo would kind of actually do the opposite of what you said. If you gave a decimal value into the modulo, it's actually going to give you, or if you did, I think if you did modulo 1, then it's going to give you just the decimal value after that. So kind of does the opposite of what you were saying.
Yeah, and that brings up a similar question. A lot of people are asking, it's like, okay, well, I can use the floor and ceiling function to round to a whole number. How would you round to, say, the nearest 1/8 of an inch or the nearest 1/16 of an inch? At that point, you'd need some.
Oh, yeah. No, that's a great question. I do want to show you how to do that. Let me add a quick, this is what I do. I add a user parameter that I call for increment. And this is where I store what the value that I want to round to. So let's say I want to round to the nearest 1/4 inch. I'll put that in here. And I make this a parameter so that I can adjust it easier later if I need to. And then I go to, let's use, not user result. Let's use A3. Change that to, oh, darn it. Change that to inches. Okay, so, and what I'll do is I'll do like this, floor, and I'll put my parameter that I want to round, and then I'll divide it by the increment, and then I'll multiply it back by the increment. So I'm doing that little unit conversion that we just had shown there, but I'm also using that at the same time to leverage the fact that I want to round to the nearest 1/4 inch. And so you'll see here 2.289, I'm rounding that down to the nearest 1/4 inch, which is 0.25. If I want to change this increment to like the nearest 1/8 inch, I can just change that to 0.125. And then, if I do something like 0.22, that's going to round down to the nearest 1/8 inch, which is 1/8 of an inch. So this is how I do that. I create an increment parameter, and then I use that little divide by and multiply by to handle the unit situation and the rounding to a specific increment.
Cool. Yeah.
Great question.
You telling me that a long time ago, and I was like, Cameron, you're a genius. So, so last question too, more of a note instead of a question. So a lot of people have been saying, especially on YouTube, asking questions about like, what are the practical applications for this? I understand that, you can do math in here. What are the practical applications? And I think understanding the math behind everything gives you a ton of power, especially when you start automating stuff. When you start automating things in Inventor, essentially you're using math and logic to be able to calculate and apply values to things within Inventor. So understanding the syntax behind all of this and how all of this functions behind the scenes helps you write code ultimately to be able to do some of this stuff automatically.
Yeah, I would just say like a quick example that, I use this stuff to like calculate geometry all the time. There's a lot of trigonometry is mostly what I'm doing. Using this for is calculating angles and stuff. So for example, if I do a support where I've got 2 vertical columns and I want to do an angled cross member in between, and I need to figure out, let's say I've got a parameter for the width between these 2 columns, but when I'm creating this actual, maybe I'm using like an angle iron here, I need to know how long that piece is. So I'm going to be using, some trigonometry based on whatever angle I want here, or maybe it's a height between here and there that I know. And that's going to help me figure out, so I can use Pythagorean theorem to help me figure out the length. But also if I want to maybe have this kind of mitered or chopped off like this, that'll help me figure out if I create a chamfer on that part to create that angled section. This will help me figure out what that angle is going to be, or maybe how thick I need to have the part be to offset it for a certain amount. Yeah, there's just lots of applications, and I use formulas for all that stuff.
Yep, and then that brings up everything with, do you do things in the parameters editor or Excel? And I think once you start automating full assemblies and part files and stuff, sometimes it's easier to manage that in Excel as opposed to the parameter editor. So keep that in mind too. But
Yeah, the parameters editor, you can do, all the math and stuff that we've talked about today, but that's pretty much the extent of it. If you start getting to any kind of iLogic, or not iLogic, but just logic, like you need to decide, okay, if this value is something, then do a specific thing, or if it's not, do something else, then you're going to need to start looking outside the parameters editor to either iLogic, or you can do that kind of stuff in Excel, have if statements in Excel that can help you control your values based on other values and that sorts of things. So yeah, Excel can definitely extend this quite a bit and give you quite a bit more power.
Yep, and then bring that into Inventor and enjoy the spoils of success. So cool. I think that's everything that we're going to go over today. Cameron, again, thanks for going through everything with us. This helps.
My pleasure.
I'm sure a lot of people found a lot of value in this. It looks like a lot of people have, just based on the comments and stuff. So again, thanks for that. Everyone, thank you for joining us today, and we'll see you again next week for Autodesk Virtual Academy. Thanks, everybody, and we'll see you next week. Thanks again, Cam.
Bye.